So it was 3:30 a.m. on July 24th when John Aldridge in Lobsterman was working alone on his boat when he slipped and fell overboard. He had no life jacket, no GPS. His boat, which was running at 6.6 knots on autopilot, was out of reach in a second. He took off his boots, turned them over, got enough air inside them that he could wedge them under his armpits and use it as a personal flotation device. And then he waited. It was 2.5 hours before his fishing buddy woke up and realized he was gone. The Coast Guard, when they got the call, went into action firing up SAROPS, which is their search and rescue software simulator. They took his last known position, ocean conditions, weather conditions, and created a series of search patterns. By 8 a.m., there were helicopters, planes, and boats spread out across the North Atlantic looking for Aldridge. There was just one problem. Not knowing the exact time that he had fallen in the water, they assumed it was sometime between when he said goodnight to his buddy and the end of his shift. And what they didn't take into account is that Aldridge was a workaholic. So he had not woken up his buddy at 11:30 p.m. the way he was supposed to. That 4-hour difference meant that he was 30 miles outside of where people were looking for him. Now, I sincerely hope that your daily work life is nowhere near as dramatic as that, but you do not have to be floating alone in the North Atlantic with nothing but your boots to appreciate that data that is old or insufficient can really make your job a lot harder than it has to be. Whether you're doing fast fault detection and remediation, you're trying to do near real-time traffic engineering, or you're just trying to keep up with the fact that with higher and higher density platforms, you have more interfaces that you need to get information about, you need a lot of data about your network's current state, and it can't be minutes or hours old. Now, this problem of monitoring has been tackled already in another domain, right? So in cloud, looking at application and server monitoring, there's been a ton of work on this, and I think it is actually one of the reasons that data centers scale the way that they do, is that they have mastered the problem of monitoring at scale. And I just grabbed some numbers from Twitter because they had a recent blog talking about how many metrics per second that they're capturing today on the server and application side. By comparison, I think networking sort of looks like this, right? And the tragedy of it is it's the data exists, right? Most of the counters and the information, the state that you want, is in your routers already. We just make it really hard to get access to it. So we know this needs to change. And when we started on the Telemetry Project, we said, let's just start with a clean sheet of paper and think about how can we solve the performance problem? How can we get as much data off the box as fast as possible? And the second problem we wanted to solve is how do we normalize to all those really cool tool changes that are already out there, right? So all this work that's in open source and all the stuff that those server and application monitoring folks are doing, can we plug into that? And finally, we knew that we would fail, right? We would try some things and some would work and some would not. And it's that experimentation that led to the lessons that I'm going to talk to you about today. Just to bring you up to date, we had our first production deployment in this year, in which we now have telemetry running authoritatively over SNMP at a 30-second push interval from the routers for a limited set of data models, but we expect the data model set to increase and the streaming interval to decrease over the course of this year. So our first lesson is that telemetry means different things to different people, right? It's one of those words like cloud or SDN that has a little fairy dust on it, so it allows you to imagine that it's whatever will solve your problem that you're having right now. But there are lots of different kinds of data in our routers. There's control plane data, like stuff about how many prefixes did I receive from this neighbor, and there's also stuff that's more related to the data plane. Maybe it's drop counters, maybe it's flow data. And we also have these incredibly wide range of timescales about how we retrieve the data, right? So some are very fast, some happen as soon as an event happens, and then some are more on the scales of minutes to hours. And a couple things that's interesting when you look at a picture like this, I think that it would hold if we looked at an even broader array of technologies, is first of all that we in networking are protocol happy, okay? Like, we want a new kind of data from a router, so let's create a whole new protocol with new serialization and templates and formats and transports, right? Not something that you'd really see in other domains. And the other thing that's really interesting is that the broader coverage that you have, the more kinds of data you can get through a single protocol or through a single method, the longer it takes to do that, right? And that was the section where we saw the most pain when we talked to our customers, was really at that. There are lots of problems in the telemetry space we could have solved. What we decided to start with was figuring out how do we get this broad set of data off the box faster than we can do it today. The second lesson is that when you throw out all the rules, it's really not that hard to beat SNMP. So in this example, the orange columns represent how long it takes for 3 SNMP pollers to get the IF-MIB from a device. And we were doing the poll every 10 seconds, polling by row, which is the most efficient way to do it. The green is that same data coming from being streamed in a push model from telemetry to 3 receivers at every 10 seconds. And as you can see, it's a factor of 10 improvement, more or less, right out of the box. And also SNMP, as maybe you've experienced in your networks, can get worse over time, especially if it cannot complete the full sequence of polls by the time the next sequence starts. Now, why is this true? You can look at it head-to-head on the wire. And this is just an example where I need 2 round trips and 4 packets to get the data using a SNMP get bulk for the IF-MIB, whereas all of that data, actually a superset of that data, because there are more counters that we deliver, can be delivered in a single UDP packet using our most efficient wire encoding format using telemetry. But it's really not about wire efficiency. I mean, that gives you some optimizations, but actually this graph was taken using our less efficient key value encoding, which takes about the same amount of space on the wire as SNMP does. So what is it? First of all, do a push, don't do a pull, right? So, every time you send an SNMP query to a device, it hits the CPU. Maybe it goes to the hardware if you're trying to get interface counters and data. Even if you're just getting software-related data, you're doing an internal IPC and you're putting load on the device. And if you have 3 requests coming one after another, it fires off those 3 processes 3 times, okay? So that's a lot of work for the router to do. Whereas telemetry, scrape the data once, put it in a packet, and if I need to make 3 copies of the packet or 10 copies of the packet to 10 different receivers, it's the same amount of load on the device, okay? So that's a way we get huge returns on performance for telemetry. And the second thing is that, SNMP is kind of hard on our poor routers in some ways, right? It has very strict semantics about, say, how you do a get next, and it also has fairly strict data models that don't really match. It's not natural for a router. So for instance, SNMP, the IF-MIB, is indexed by IF-index, whereas for a router, we index by the interface name. Okay, so trying to match interface name to IF-index can be, it's just extra work that you put on the device. So if we just get rid of that and say, look, we're going to grab the data in a way that's natural for the system, then we can get real performance improvements there too. So lesson 3, I think, is true of all relationships, whether it's with another person or with a protocol. And that, you can talk about what you hate about SNMP all day long and how it's a performance bottleneck, but when it's gone, then you're suddenly like, well, how do I find out what the key is for bytes received on a particular interface? And so one thing we did to get that efficiency is we really went into the internal, looked at how the data was stored internally, and we exposed that with as little abstraction as we could to the external user. So if you see that not so well-known name on the bottom there, that is a representation of how the data is stored internally. And could you figure out that? We gave some tools for introspection, but it was a fairly painful process compared to having a well-known OID that you can look up on any box that supports that MIB. So that sort of led to lesson 4. Once we solved the performance problem, it's like, okay, well, hang on. What we really need here are some data models. And the first step to that was to use, I think the industry is pretty much converging on Yang as a way to model data. And Yang has many benefits over SNMP. One of the most important things is that it allows you to order by system, right? So you're not forced to take the order, say, that a MIB wants you to use. You can just use whatever order the data is, however you store it. So we have vendor-specific MIBs, obviously. We have, the vendor-specific one here is an internal representation of a Yangification of our interface data. But then we also are working on vendor-neutral models for that same data. So in particular, this is some work we've done to start streaming data in the OpenConfig Yang model as well. So lessons we have learned here are really that some models are harder than others. We've been working on OpenConfig and IETF models for both config and opera data. And config has an interesting set of problems around impedance mismatch. So essentially, if one model has a parameter that's at one level in the hierarchy, and another model has it at a lower level in the hierarchy, you can have a one-to-many mapping problem there, which you have to, the router then has to keep track of state, and it has to figure out how do I map this leaf to that leaf, and so on and so forth. That's really a config problem. For opera data, it's mostly stateless, and it's mostly pretty easy to map between models. On the other hand, there's still a scatter-gather problem, in the sense that we may define a vendor-neutral model that takes data from multiple internal models. So we have to scatter the query and then gather the results back and populate the model. Okay, so that can be resource-intensive to do that. And we've had to think a lot about how do we optimize the software architecture to make that go fast enough for the demands of telemetry. And ultimately, and this applies to every vendor-neutral model that you deliver, is that the development cycle might lag, right? We might deliver some incredibly cool new feature that has new parameters. There will not be an OpenConfig model for that for a while. So how do we deal with that problem? Filtering is a really interesting question. We are talking about really massive amounts of data. And just to give you a simple example, a couple of months ago, we did a demo Friday with SignalFX, who's a cloud monitoring partner. And we wanted to just do a very simple demo that showed the amount of traffic going out of a tunnel interface, RSVP-TE tunnel interface, and compare it to the auto bandwidth setting that was the router was adjusting the size of the tunnel to dynamically. And so essentially what I needed from that tunnel were two parameters. But if you looked at the internal struct that we maintain for a TE tunnel, there's something like, 300 leaves in there, right? I could, if you imagine streaming 300 leaves for every tunnel on the device every 10 seconds, that's a lot of data, right? And so it was very useful to be able to write a filter on the box and only send the couple of parameters that I wanted there. So, but it's always a trade-off, because internally in the system, bulk data collection is efficient, right? If I just go and grab the whole bag of data, I can do that very efficiently. But processing it and putting it in the wire is not so efficient. Once you've filtered, you don't get that data back, right? So if you go back and say, oh, I really wish I had known this other parameter about my TE tunnel at that point in time, you don't have it. So you're going to have to think about, do I do the filtering on the device, or I do it on the collector? The other thing that we learned is that self-describing data has pros and cons. So what I mean by this, again, when we started off with our number one goal of being highly efficient, as performant as possible, we said, well, what's the most efficient way to do that? We chose a binary encoding to start with, Google protocol buffers, and we did what is called a compact encoding, or what we call a compact encoding. So this is essentially like, if you think about it, it's represented as a key-value pair, and the key is an integer. And then, that integer describes what the value is. In order to decode that, for example, to know that 50 actually means packet sent, you need a decoder ring, you need a protofile. That protofile has to be shared between the collector and the router, and that's some operational overhead. All right, so what we discovered when we first delivered this to a customer, they sort of looked at it and they're like, well, I don't really want to be managing 50 protofiles from your router. Another customer looked at me and said, are you kidding? Compared to trying to compile MIBs, this is nothing. So I guess complexity is always in the eye of the programmer or the beholder. So the next thing that we came up with, we experimented with, was we call it Google Protocol Buffer Key Value, or self-describing. It's very similar to JSON, if you know that. So it's self-describing in the sense that we tell you what the key is. So we give you the key in a string. At the same time, we give you the actual data, right? And so that looks friendlier to a human eye, but strings are not particularly efficient, not in terms of being able to process them, and they're not very efficient on the wire either. But it can be a useful thing if you don't want to be managing protofiles. So we have both options today, and I think it will be really interesting to see as more and more people adopt this, how different people interpret the trade-offs between the two. So our 8th lesson is that transports have trade-offs, right? This is not anything new to anyone here. Again, high performance data, we started with UDP, right? We can cram all of that with that compact GPP encoding, we can cram all that data into a single packet, and that's great, right? That's the most efficient thing that we can do. And if you look at that little table up there, that score of 100% is measured in sort of laws of physics, maximum number of metrics per second, if you're SNMP guy, OIDs per second, that I can get off the box. So the very fastest we can do this is using that really compact binary encoding and to do it over UDP. But there are obviously problems with UDP, right? You can't fragment it, so if you have a table that cannot be compressed to fit inside a UDP packet, you can't send that table. There's not that many of those that we discovered, but there are a few. Obviously, your packets might get lost. It's insecure, but it's very fast. Okay, so that's what's appealing about UDP. We also initially came out with TCP, and these are just raw sockets, right? So if you're a Python programmer, you just bind to the UDP port or you bind to the TCP port, you're getting a packet and it has the object with the data in it. So TCP is nice, obviously you can fragment it, guarantees your delivery, but it is very vulnerable to loss. And I mean, this is a chart we did, but it's any graph that you do about loss in TCP sessions. So if you have a lossy network, or your network becomes lossy right when you most need that monitoring data to come back to you, then this could be of concern. As a third type of transport, and actually more than transport, we also implemented gRPC, which is based on HTTP2 with an RPC mechanism that goes around it. And there, I think, are two main motivations that people might be interested in using gRPC over a raw socket, a raw TCP socket. The first of all is if you are already doing your management, like your configuration management using gRPC, like you're sending a Yang model over gRPC to do config, then being able to set up this bidirectional streaming and get the operational data using the same protocol as you're getting your config data, then that might be appealing to you. The other thing that it gives you is security. Optionally, you can turn on TLS. So if you're worried about the security of your monitoring data, you can use that. And really, if you have hardware offload for encryption, there's no impact to performance. The 9th lesson is that it's time for the rest of us to start thinking about what the analytics pipeline and the platform is going to look like. The first customers that we started working with telemetry were folks who had, by and large, had a ton of experience already with that monitoring at scale from their experience in the data center. So they had already built tools. They knew how to store, manage, stream, visualize huge quantities of data. So for them, they didn't care, right? They're like, thank you very much. Give us our JSON object, show us the proto file, and we'll see you later. We've already built our collector. So that's great. That's the kind of BYO approach to building a collector. I don't think everybody can really do that. So one of the things that we did is that we created some open source code to sort of get people up and running quickly. You can do a proof of concept. We put this in GitHub, and this enables you to stream telemetry into like an ELK stack. How many people here know what an ELK stack is? Okay, so a few hands. There are Prometheus or InfluxDB. These are all open source databases that you can put data into and then run some nice applications on top of. And I would say that for the rest of you, if your only experience with open source code has been around like network tooling, you should really check out what's going on in the big data analytics platforms, because there's some really good stuff in open source. There's a very vibrant community. I know we've been talking about, how do we get more young people into this business and interested in doing this stuff? Well, they're doing it, right? They are in those open source communities, and they're working with these kind of tools. So we have some code in GitHub, so you can try that out. I think ultimately also, people have their tools that they like, that they're already using. We were able to do pretty easily with SignalFX and some other partners an integration. It's typically a very small thing to integrate with almost every tool if you have a JSON object or a protobuf. It's no big deal to put that into third-party applications that allow that. Okay, so GitHub, if you're interested, I'll send out the link to that. The last lesson, I actually had way more than 10, but 10 lessons for telemetry has a nice alliteration to it, and I couldn't talk forever, so I just kind of capped it at 10. Maybe we'll have some time for questions to look at some of the other ones. But lesson 10 is that lots of data is good, okay? But diverse data from different sources, is more than the sum of its parts, okay? So to the first point that lots of data is good, here's a very simple use case that got one of the folks that we're working with excited about telemetry. So this is this classic problem. You're running an application across a network or a service of some kind, and part of that network you own and part of the network you don't own, okay? And you could do the inverse of this use case. So there's a black box somewhere in your network that you have no way to get data out of. And so your application monitoring service starts telling you that you have drops. And what do? Well, you look at your own network, and you say, no drops here. So either there's a bug in your code on your routers that's not catching the drops, or there's a bug in the application, or there's something going on in that black box. So what you can do, what they had done, even just using SNMP, is look at the packets sent on one side, compare that to the packets received on the other side. And obviously, this is not simple subtraction, right? Because there's tens of thousands of packets going through there all the time, and you can't precisely correlate your timestamps the way you want to. But if you have a minimum amount of traffic, you make some assumptions about the data, you can do a linear interpolation on that data. And they were able to detect drops on the order of, say, 10% over a 5-minute interval using that data. Well, if he could get that sort of results, getting data every 5 minutes, then think what he could get getting that same data every 30 seconds or even every 10 seconds. You start to move to polynomial interpolations, and then things start to be a lot more accurate. So incredibly simple use case of just getting more of one statistic. But I also think that diversity is important, data from different sources. So in one sense, one of the things that people are most interested in is not just stream me telemetry data, but can I get that along with my topology data that I'm getting through BGPLS or BMP? Can I combine that with flow data? Can I combine that with segment routing traffic matrix data? And the answer is yes, and I think it is when you combine many different kinds of networking data, that goes back to my first slide, that things start to get interesting. And then there's a set of really forward thinkers who are saying, you know what, let's break down these silos between application monitoring and network monitoring. Let's merge these data sets and find ways to reason across both of them at the same time. This could be for monitoring and troubleshooting, and we've seen presentations on this at this forum now and in previous sessions. But also, ultimately, maybe to give the application enough visibility on the network that it can also do some control. So in conclusion, telemetry is real, but it's not done. There's plenty of work that we still have to do, and lots of areas in that spectrum I showed you in slide 1 that we still have to investigate. Performance is absolutely paramount until you solve that problem. And then other problems, like how are you going to model the data, how are you going to encode it, what's the right transport, then become important. And then my final plea would be don't reinvent the wheel. There's a ton of great stuff out there for doing monitoring at scale, and we should reuse and build on what's already there. And finally, if you're having a really bad day, I want you to remember John Aldridge, okay? So there he was floating in the ocean. Mid-morning, his partner is sailing around trying to find him, and he notices something out of place. That ice chest shouldn't be there, and there's a handle that's been ripped off, and he sees it in his mind, how his buddy reached down to jerk the ice chest, and the handle broke, and he flipped over backwards into the water. And he also realizes that his buddy would not have been moving that ice chest at 11:30 at night. It must have been much later that he actually went into the water. So he gave that data to the Coast Guard. SAROPS reran the simulation. The search moved south. And in fact, his fishing buddy in his own boat came within 1/4 of a mile of John Aldridge at one point, and he didn't see him. So by 2:30 p.m., things were looking really bad for John, right? So he'd been awake for over 24 hours. He'd been in the water for 12 hours. And the Coast Guard helicopter called in that it had fuel for one more search pattern before it had to return to base and be grounded for the day. So the Coast Guard calls back and says, "We're sorry, SAROPS has crashed. We cannot give you a search pattern." So the duty officer at the Coast Guard station looks at the last map they had from SAROPS, takes his finger and draws a line across it, and then up to the Coast Guard station. And he says, "There's your search pattern, guys." And so it was 30 minutes later that the Coast Guard rescue swimmer rescued his first ever live person from the ocean. John made him go back and get his boots. And why I love this story, because what it says to me is that even with imperfect data, the greatness of the human spirit and a little bit of luck together combined can make incredible things happen. Now, I think it is sad in some ways, great and sad, that our networks run on those same principles some of the time. We can and should make it easier on ourselves, and the way to start doing that is by streaming more of our operational data out of the network using telemetry. Thank you. Any questions or feedback or thoughts?
Matt Petak, Yahoo. This is impressive. This is something that we've been doing a lot of looking into. So far, none of the code you're talking about, those in production versions of releases, this is all lab work. Is there kind of a time frame for when you think this is going to be ready for production releases of code?
So we had a limited production release for basically one customer that we shipped out last year, which is what is being used right now for the production deployment. For our NCS 5508 platform, this code came out in December. It was shipped in XR 6.0, and you should see it in other XR platforms into the summer.
Good, thank you.
Okay, thank you.
Tony Tauber, Comcast. You know, this stuff, to me, it seems like, you know, probably nirvana, which is nice, but obviously we're all going to be living in, you know, feet in all parts, you know, all different quadrants, like SNMP, SNMP only devices, SNMP only tool chains, you know, telemetry devices, telemetry tool chains. So, you know, GUI and stuff to make the things talk to each other and publish in arbitrary formats or fetch in arbitrary formats, I think is a good challenge to the open source community to try and create that translation. So,
yeah, it's interesting. I actually talked to a customer several months ago. When I started talking, he's like, "Oh, you know, I spent one weekend and I built a converter that takes a MIB and transfers that into a JSON object because all the other tooling in my data center uses JSON objects." And so I don't think it was an open source, but I think there is a great need for that to, you know, think about legacy devices as well. And our first customers have said we're going to run both for a while, right, until we feel that, you know, we can authoritatively use one over the other.
Yeah, and the devices won't, you know, there's a lot of devices that won't ever do the new thing. So.
Right. So new technologies are hard. Yeah.
All right. Thank you very much.
All right.
Appreciate
Thank
that.
you.